Good morning, everybody. Today we will continue with X-ray resonant magnetic scattering. This is completely new method compared to the other applications of X-rays, which we have discussed during the last lectures. With that method, we can investigate the magnetic properties of the materials. By using X-ray diffraction, X-ray reflectivity, you can investigate structural properties of the matters. For example, thickness analysis and roughness and surface roughness, interface roughness of the materials, density of the materials can be checked by using X-ray reflectivity, and Miller indices crystal quality, and also the lattice parameters, interplanar distance can be obtained by using X-ray diffraction. So with this method, we can determine the magnetic properties of the materials. So what we have here, we have a material, but now it is a magnetic material, again thin film, okay? Here we have an incident photon. It comes with some certain angle to the material. This is the sample angle, theta. And then it is reflected with same theta angle to the detector. So this is taken in specular geometry. So we get magnetization, we get information about the magnetization of the sample. So what we have, what are the advantages of that method? We can determine the magnetic properties of interfaces and multi-layers. So if you consider that you have a multi-layered thin film like this, let's consider here we have silicon substrate. Here we have iron, for example. Here we have nickel. Here we have cobalt. Here we have platinum, let's say. And here we have another type of material. Again on silicon. Here we have iron cobalt alloy, and here we have platinum top layer. So by using that method, we can determine the magnetic properties of cobalt, magnetic properties of nickel, magnetic properties of the iron separately, okay? So this is the main advantage of that method. This is element specific, and we can determine the magnetization of each layer selectively. In addition to that, if you have an alloy, for example, here, alloy from iron and cobalt, let's say 50% iron, 50% cobalt we have here, so we can determine the contribution of the iron and contribution of the cobalt to the magnetization of this layer. This is very, very powerful and unique method to study magnetization of the magnetic materials. Since we are dealing with magnetic materials, we can apply magnetic field during the measurements of XRMS. And as I told you, the magnetic hysteresis of each layer, each magnetic layer, can be determined specifically. What about the geometry of the measurements? So this is normal specular reflection geometry, as we have used in X-ray diffraction and X-ray reflectivity experiments. But in addition to that, we apply a magnetic field in the sample plane, okay? So due to the magnetic field, XRMS measurements uses Elmore geometry. I will talk about this. So before giving information about Almog geometry, let's consider what is MOC and what it means. So we are talking about magneto-optical effects. So what is a magneto-optical effect? Here we have a polarized light. It can be laser, or for our case, it is X-ray, okay, polarized X-ray, which is coming from the X-ray source, and it goes to the detector. The detector is waiting there, and here we have a transparent material. Okay, let's consider. If this material is magnetic, and if this X-ray beam or laser beam is polarized at the beginning, so after passing through that magnetic material, the initial polarization of the light is rotated with some angle, which is given by Faraday angle, theta, Faraday. Okay, we have polarized light, polarized X-ray or polarized laser light, and here we have a magnetic material, and this is transparent. X-ray or laser beam can pass through that material, and after passing that material, the initial polarization, this is the initial polarization of the light is changed with some angle, which is called as Faraday angle. This is called as Faraday effect because it is discovered in 1845 by Michael Faraday. Magneto-optical Faraday effect. Then in 1877, John Kerr discovered that more or less the same mechanism works for the reflected light. Okay, he used another material which can reflect the laser light. Okay, then he also used polarized light. Here we have polarized light, and it is reflected from the magnetic material. Then the initial polarization of the light is rotated with some angle, which is called as Kerr angle now. Okay, then this effect is called as magneto-optical Kerr effect, and shortly MOC. Okay, magneto-optical Kerr effect. In 1985, this effect is also called as surface magneto-optical Kerr effect because this method is surface sensitive. It can take information from the surface around 20, 30 nanometer, depending on the type of the material. So this is the magneto-optical effect, magneto-optical Faraday effect, and Kerr effects. So now let's talk about different geometries for magneto-optical Kerr effect. What we said here during XRMS experiments, we use Almog geometry, okay, this one. So what is the difference between other geometries of Kerr effects? Here we have three geometries. One is polar MOC, the other one is longitudinal MOC, the other one is transverse MOC, LMOC, TMOC, okay, this short name. So what we have here in polar MOC, this is the material, thin film, let's consider. This is the incident light, reflected light. And this is the magnetization of the material. In case of magneto-optical measurements, of course, the films, materials, samples have magnetization, okay? So in case of polar MOC, the magnetization of the material is perpendicular to the film surface. This is the sample plane, and this is the scattering plane. Incident beam and reflected beam form the scattering plane. This is the scattering plane. So what do you see here? That the magnetization vector is perpendicular to the sample plane, but it is parallel to the scattering plane, okay? In case of polar MOC. In case of longitudinal MOC, what we have here, magnetization is in the film plane, so it is parallel to the sample plane. What else? This is the scattering plane. Magnetization is also parallel to the scattering plane. Okay, this is the longitudinal MOC geometry and widely used to investigate magnetizations of thin films in the film plane. And there is another method, which is called as transverse MOC. Here, in that case, again, we have magnetization in the film plane like this one, but the magnetization vector is perpendicular to the scattering plane. You see, here magnetization is parallel to both sample plane and scattering plane. But here magnetization is parallel to the sample plane, but perpendicular to the scattering plane. This is the main difference between LMOC and TMOC. So for the X-ray resonant magnetic scattering experiments, we use that geometry. So now let's continue with the XRMS measurement setup. This setup has been designed and installed by Johannes Grabes, former PhD student of my professor in Germany, and he did very nice job on this, and you can find the details in that paper. So what we have here, this is a diffractometer. Okay, you have seen many types of diffractometers in previous lectures. So we have a sample holder here, okay? We have detector here, and here we have X-ray source. We have seen the synchrotron light source. This type of experiments have been done in the synchrotrons because you need monochromatic X-rays and you need to change the wavelength of the light. So here we have electron gun, microtron, booster or synchrotron accelerator. Then here we have storage ring. Here we have undulator, monochromator, beamline, and end station. So this is the end station. Okay, here you see the picture of the synchrotron Bessey 2 in Berlin. So here we have a diffractometer. This is the incoming X-ray beam. This is the sample. This is the reflected X-ray beam. And here we have detector, X-ray source, detector, and sample, okay? Like normal diffractometers. But in addition to the normal diffractometers, here we have a magnetic field source. Okay, so you can apply magnetic field parallel to the sample surface. You can change the direction of the field also in the film plane, and you can change the position of the magnet. You can change the theta angle between X-ray beam and sample surface. You can change the 2 theta angle of the detector. You can also change the direction of the magnetic field, okay? Because this electromagnet has also axis of freedom. You can change its position by using computer commands. So what else we have? We have a load lock window, okay? Then you can open it and put your sample in and then close it. So all the system here under vacuum conditions. So about 10 to minus 7, 10 to minus 8 millibar. So another option of that instrument is that we can cool the sample down to 4.2 Kelvin, okay, liquid helium temperature, and we can heat the material up to 475 Kelvin, okay? So you can change the temperature within very wide range. We can apply magnetic field up to plus minus 2700 Ørsted. And what else here I can tell you? So you can change many parameters. Very nice goniometer, very nice diffractometer. And the name of this diffractometer is Alice diffractometer, and it is located in Berlin at Bessey 2. Okay, now what we can do with that diffractometer? We can change the polarization of the light. Here, the X-rays are coming from undulator and monochromator through the beamline to the end station here. So we can change the polarization. You can use linear polarization or circular polarization. And we can change the energy of the X-rays, incoming X-rays. I mean, you can change the wavelength. This is very important property. And we can change the sample and detector angles. We can change the magnetic field. We can apply magnetic field. We can change the direction of the magnetic field. And we can also change the position of the magnetic poles. And we can change the temperature within that range. So you see that with one instrument, we have many freedom. So these are very important to investigate magnetic materials. So now let's continue with polarization. So what is polarization? What is linear polarization? What is circular polarization? This is the sample, okay, sample plane you see. And then this is the scattering plane. The incident beam is coming like this to the surface of the sample and then reflected like this. So this is the scattering plane. So in light, we have electric field component of the light, we have propagation vector, and we have the magnetic field component, right? So in order to show the polarization of the light, we deal with the electric field component of the light. So if the electric field component of the light is perpendicular to the scattering plane, then it is called as E sigma, okay? E sigma incident. If the electric field component of the light is parallel to the scattering plane, then it is called as E pi. So here we have E pi final, here we have E sigma final and K final. So E sigma is perpendicular, E pi is parallel to the scattering plane. So in order to get linearly polarized light, you have to choose one of them. And you can do it by using the undulators. So then what is circularly polarized light? Circularly polarized lights contain both components of E sigma and E pi here. E sigma plus minus I, E pi. Then here we have again a plus minus sign. Here we have minus plus sign. So the positive and negative signs here show the right and left circular polarizations. So if you have positive here, it means that this is right circularly polarized light. Here you have minus and here we have positive. If we are talking about the left circularly polarized light, then here we have E minus, positive here, and then negative here. So this gives us information about linear and circular polarization of the light. So we can do this by using the properties of the synchrotron light source. In addition to that, we can change the energy depending on the material under investigation, depending on the element within the layers of the thin film. We can change the energy because here we have monochromator on the beamline, right? So we have this flexibility in synchrotron light sources. So, but which energy? Here we have table for electron binding energies in electron volts. For example, for the oxygen, the binding energy of the electrons for the K shell or 1s shell, we have 543.1 electron volt. If you are investigating titanium, we have binding energies like this, but of course, the energy range of each beamline is limited, okay? So usually, let's say, less than 1 kilo electron volt. So then below the 1 kilo electron volt, we have that energies for the titanium, for example, okay? 460 electron volt, 453 electron volt, something like this. If you are measuring the iron, for example, so this energies 719, 706 electron volt. If you are dealing with cobalt, 793.2 and 778 electron volt. If you are dealing with nickel, this energies. If you are dealing with zinc, for example, this energies, okay, above the 1 kilo electron volt. So depending on the element under investigation, we can change the energy. This is very nice property of the XRMS method. Then, as I told you, we can change the sample and detector angles. We can change the magnitude and direction of the magnetic field. We can also change the temperature within a wide scale. So with that flexibilities, with that freedoms, this instrument is very, very useful for many different materials to investigate their magnetic properties. So now let's start with the X-ray magnetic reflectivity. During the last lecture, we have seen X-ray reflectivity. So what is X-ray magnetic reflectivity? Everything is same except the energy and the magnetic field. So we have soft X-rays here compared to the normal X-ray reflectivity. In addition to that, we will apply magnetic field to the sample plane. So how to carry out that experiments? First of all, we choose the polarization. This is very important. Set the polarization and then set the temperature, okay? And then select the energy depending on the element under investigation here. For example, if you are investigating the magnetization of cobalt within that system, you have to choose the energy of the cobalt here, this one or this one, okay? You select them, then fix that energy during this measurements. We usually choose K, L2 and L3 energies. Then we are doing sample alignment as we have done for the X-ray reflectivity experiments. So after the alignment, we can carry out two types of measurement. One is that you apply magnetic field and then measure the reflectivity. So then you change the polarization of the light and measure another reflectivity. Or you can do like this. You can fix the photon polarization and then apply magnetic field in that direction, measure reflectivity, reverse the direction of the magnetic field, measure the reflectivity again. This is this is another possibility to carry out these experiments. If the material is magnetic, then there must be a difference between two reflectivity curves. So here I will show you. This is the result. This is 2 theta angle in degrees, okay? And here, this is the intensity read by detector. So what we have here, we have two curves. One is black one, the other one is red one, two intensities, okay? So they look like same. So what is energy? Energy is 780 electron volt. Look at the table, 780, so around the cobalt L3H, okay? Because here we have zinc cobalt oxide on aluminum oxide. We have investigated that material by using XRD in previous lectures. So you already know that system. So we would like to investigate magnetization of cobalt here. So then for this reason, we choose the binding energy of the electron for L3H. Then we set the temperature. Temperature is 300 Kelvin, okay, around room temperature. Then we select polarization. We usually choose right circularly polarized light. It is shown by sigma plus. Let me write it here. This is right circularly polarized light. And then what we are doing, we apply external magnetic field in that direction to the right. Then we take one reflectivity curve as a function of the 2 theta angle. And we reverse the direction of the magnetic field and we measure another reflectivity curve. And we record the intensities for both measurements, okay? So what do you see here? Is there any difference between the reflectivity curves? You can see a little bit, you can see some differences here, but not so much, right? So they look like same. But what about in reality? In order to see the real differences between the two curves, we have to plot a symmetry ratio as a function of 2 theta angle. This scale is same, but the y scale is different now, asymmetry ratio. What is asymmetry ratio? This is the asymmetry ratio R. Here we have intensity minus intensity plus over the total intensity given by intensity plus and intensity minus. Okay, this is the asymmetry ratio. If you plot that two curves in terms of asymmetry ratio, then you get that type of signal. What we have here, we have more or less no difference between two curves. It is around zero. It is also more or less zero around that angles, and it is zero around that angles. You can consider like this.
Bir şey soracaktım ama.
Tabii, buyur.
What is I plus and I minus? I don't understand.
Okay.
I can't see.
Okay. So let me explain I plus, I minus here. So here we have an X-ray source. X-ray beam comes from the beam line, okay, let's consider. And then here we have detector. Detector records the intensity, right? So this is the intensity scale. So we change the theta, 2 theta angles, okay? Theta, 2 theta angles. And then as a function of the 2 theta angle, we record the intensity, like in X-ray reflectivity measurements. And detector records the intensity. I think this part is clear. But then what is I plus? What is I minus? So for the first measurement, which is shown by the black color here, I apply magnetic field in that direction, and then I measure the reflectivity curve. I measure the intensity plus at the detector. Then I reverse the direction of the magnetic field. I apply magnetic field in that direction, and I am repeating the reflectivity curve here again. So I record the intensity at the detector. Now I call that intensity under reversed magnetic field is I minus. Okay, so I minus and I plus are the intensities recorded for different directions of the magnetic field applied parallel to the sample plane. So now let's continue to discuss the asymmetry ratio here. What we see within that range and that range, we have more or less zero. There is no difference. Asymmetry ratio shows us the difference between two curves. But here in that range, we have huge difference between two curves if we plot it in asymmetry ratio. So first of all, here we have a peak on the positive side, and then it goes to the negative side. Here we have more or less a 12%, okay, and then it goes to zero. So there is no difference here, more or less no difference within that range. So what is the meaning of that? If the material is not magnetic, it must be like this, a line around the zero, okay? But here we have huge difference between these two curves. And how to use that information? So for the forthcoming real XRMS experiments, we have to choose a position for the detector, okay? So let me draw it again. Here we have incident X-ray beam comes from the monochromator, from the beam line, and here we have the detector, okay? So this is the theta angle, and this is the 2 theta angle. So in which angle, at which angle we will continue to that measurements? So what will be the angle for the forthcoming measurements? So in order to determine this, we will use that information here. Look at this one. Here we see maximum signal. Let me draw. So let's say 8.2 degrees, okay? We also see maximum signals here in negative direction. Let's say it is around 11 degrees, okay? So which angle is good for us? 2 theta 8.2 degrees or 2 theta 11 degrees? Which one is good? We prefer that one, I mean that position. Why? Let's have a look. 11 degrees somewhere here. Okay, and then 8.2 degrees somewhere here. What do you see if you compare the intensities for both angles? This is the intensity recorded when the 2 theta is located at 8.2 degrees. This is the intensity recorded when the 2 theta is 11 degrees. You see, the intensity is more or less 2 times higher compared to that angle. And here we have huge difference in terms of magnetization. Then we prefer that position. So it is also explained here. We select the position where the difference between the curves and the intensity are maximum. So as you see here. Any question here? Did you understand that point? Okay, we have carried out X-ray magnetic reflectivity measurements, and then we have found that this position is the best for me to continue, because at that 2 theta and theta angles, I can get the maximum difference between two curves, okay? And then I can get the maximum signal at that angle, maximum intensity, let's say. So now let's continue with X-ray resonant magnetic scattering experiments. This one we will carry out. So how to carry out such experiments? First of all, just go to the best angle, which we determined from the X-ray magnetic reflectivity experiments, where the difference and the intensity are maximum, and then set the temperature, set the polarization, and scan the energy, like this one, energy in certain range. Then change the direction of the magnetic field, again scan that range, okay? And then another option is that fix the direction of the magnetic field, and then by changing the polarization, you can carry out same experiments. Here we have XRMS scans for cobalt L3 and L2 energies for a fixed polarization. We use right circularly polarized light here, and then 2 theta angle is equal to 8.2 degrees, then theta angle is 4.1 degrees, temperature is fixed at 300 Kelvin, okay? And then we have energy range between 720 and 840. Why this range? If you would like to investigate cobalt within that material, you have to catch the energies of cobalt. Here we have 778 for the L3 edge and 793 for the L2 edge, right? So you have to see that energies. So here we have this one, 793.2, and here within that range we have this one. So if you start earlier and if you finish later on, so then you can see that range of the cobalt L2 and L3. Let me draw the measurement geometry again. This is the incident X-ray beam coming with theta angle. This is 4.1 degrees and goes to detector. Okay, we apply magnetic field in this direction, or we can reverse it. So then we scan that energy range. So how to scan that energy range? We can do this by using monochrometer, okay? In the beamline of the synchrotron light sources, we have monochrometers, so we can change the energy of the incoming X-ray beam. So we apply magnetic field along the positive side, let's say, okay, this is the direction of the external magnetic field applied in the film plane, and then we change the energy range. So we scan the energy range, and then we record the intensity at the detector, okay? So intensity is recorded here. So then here we have intensity plus, shown by the black color here. Then I reverse the intensity. So I reverse the direction of the magnetic field, shown by the red color. Then I scan the same energy range again. So what do you see here? That the intensity recorded under reversed magnetic field is different, especially around L3 and L2 edges of cobalt material here. You see, you can see huge differences here. There is also difference. This is the maximum of the black one. This is the maximum of the red one. This is the maximum of the red one. This is the maximum of the black one. So we have also features around that L2, L3 energies. So it means that you have magnetic signal, but as we have done for X-ray magnetic reflectivity, if we plot a symmetry ratio, we can see the difference between two curves here. The difference between two curves can be seen better if we plot a symmetry ratio. Here I will show you a symmetry ratio, but before I go to a symmetry ratio, I would like to shortly touch another information. What you see here, the intensity for that energy is much higher than the intensity recorded for that energy. So what is the reason for that? And if you apply magnetic field to the right side, we have higher intensity than the XRMS signal measured for the opposite magnetic field. But for that energy, the intensity for the opposite magnetic field is higher than the magnetic field applied to the right side. So what are the reasons of that features? I will not go into detail within that part of my lecture, but during the next week, we will continue with X-ray magnetic circular dichroism, and I will discuss all the details of that features within XMCD course. So now let's plot the asymmetry ratio of these two intensities. Here we have the asymmetry ratio, okay? So what do you see here? Until we are coming to the cobalt L2, L3 energies, we see more or less no difference. Actually, there is no difference here. And also after passing the L2, L3 energies, again, we have more or less no difference. Asymmetry ratio oscillates around 0, okay? So you can also see it here. There is no difference here. But between the energies of L2 and L3 for the cobalt, or within that range, what do you see here? That we have huge difference between two curves, and this difference reaches to more or less 30%. Okay, here we have goes to more or less to 18%, something like this. So we have huge difference between two curves. So it means that cobalt is magnetic here. This gives us magnetic information about the cobalt. But in addition to cobalt, here we have oxide and zinc elements, okay? What about their contributions to the magnetization? We know that the pure cobalt metal in periodic table, if you consider cobalt element, cobalt is ferromagnetic and it should give magnetic signal like this. It is expected. But oxygen is paramagnetic, okay? It is not expected to give such signal. And zinc is not magnetic, okay? We don't expect any signal from the zinc, but I would like to be sure, and I will investigate both oxygen and zinc elements because this method is very useful. This is element specific, okay? If you consider other conventional magnetization measurement systems, magnetometers, you can only measure the magnetization of the whole system. But by using XRMS method, I can selectively measure the contribution of that element, and that element to the magnetization selectively. So then let me do that. Here we have another XRMS experiment. This is the energy range, okay? Starts from 500 electron volt, it goes to 600 electron volt, and we are looking for the oxygen. Let's go to the table for the electron binding energies. For the oxygen, the binding energy for the K shell is around 543 electron volt, okay? 543. So I have to scan that range. 543 is around here. So I should start earlier. I should finish later. Okay, then I can change the energy in order to see the oxygen K shell. So I apply magnetic field in that direction and I measure the intensity plus. I change the direction of the magnetic field. I measure intensity minus. What do you see here? There is no difference. You cannot see something in XRMS signal, right? But if I plot a symmetry ratio from that two signals, I can see this information. A symmetry ratio clearly shows us that we have a magnetic signal from the oxygen. Of course, it is very small compared to the magnetic signal from the cobalt. Here we have 30%, here we have 0.6%, less than 1%, but it is a real signal. It is not a noise. We have many data points here. So what is the meaning of that? If you remember that before cobalt ion implantation, here we have zinc oxide, right? And then we implanted that system with cobalt ions, and cobalt replaced by the zinc atoms, or this was the idea, okay? So if the cobalt atoms are replaced by the zinc atoms, then there will be a relation between cobalt and oxygen atoms. So we can talk about cobalt oxygen bonding, okay? So since cobalt is magnetic, then it affects the oxygen P levels. Oxygen P levels are splitted due to the magnetic neighboring cobalt. Then we also see signal from the oxygen. So this is very nice and very useful data. You cannot get this data by using other methods. So we can clearly show you that the cobalt sits on the zinc oxide lattice and makes bonding with oxygen, neighboring oxygen atom. So now let's also try to investigate the zinc. So what about the zinc energy? Zinc energies are around here, more than 1 kilo-electron-volt. Hopefully in that time, energy range of the beamline was okay for us. Then we have also investigated zinc edges. So here you see starting from 1000 electron volt to 1070 electron volt. What do you see here? I plus, I minus. We apply magnetic field and recorded intensity as a function of energy and reverse the direction of the magnetic field, recorded intensity again. The resolution of the signal is very low because we are almost at the limits of the beamline energy range. And what else? If we plot the asymmetry ratio for both signals, what do you see? 0. There is no signal from the zinc and it is expected. So XRMS is very useful, very nice, very powerful method. You can study the magnetic properties of the elements selectively by using the advantages of synchrotron light sources. You have huge intensity in synchrotron light sources, and you can also manipulate the incoming energy of the X-rays. So now let's continue with another important advantage of XRMS experiments. We can carry out hysteresis curves. Hysteresis curves are characteristic features of the ferromagnetic materials. So by investigating that curves, you can get information about the magnetic properties, okay? Magnetic properties are used everywhere for many applications, for technological applications, for scientific applications, for industry applications. We use magnetic materials everywhere, and depending on the application, we need different properties of magnetic materials. For example, if you would like to use this type of materials as a permanent magnet, then we need high coercive fields, okay? And we need hard magnets. But if you would like to use that type of materials in magnetic sensors, then we need low coercive fields. We need soft magnets. So hysteresis curves can give that information about the magnetic materials. So how to carry out hysteresis curve measurements by using XRMS method? First of all, we go to the best angle, which we determined from the reflectivity curve. Here we have carried out reflectivity curves and then determined the best angle, okay, where the intensity and the magnetic difference are maximum. So now we set the angle, then we set the temperature. This is very important in every type of measurement, okay? In order to avoid the oscillations on the data, you have to set the temperature. Then we select the polarization, and then we also select the energy depending on the element under investigation, okay? So polarization is fixed, energy is fixed, and then we scan the magnetic field now, okay? I will show you. So here we have material. Again, incoming X-ray beam is coming like this with certain theta angle, and goes to detector with certain 2 theta angle, okay? Then we record intensity as a function of magnetic field. What do you see here? We have a magnetic field source, and we increase the magnetic field in positive direction, and then we decrease it and we increase it in negative direction. So we scan the magnetic field. So here you see 2 curves. One is black one, the other one is a red one. Black one is taken for cobalt L3 energy. It is around 773.4 electron volt. Let me show you. Around this energies, okay? Around this energy, somewhere here. You can also take somewhere here, but I'm showing the data taken at that energy. And the red one is taken around the oxygen KH around 526.8 electron volt, 526, 25, 26, around that maximum, okay? Data is taken. And both data are taken at room temperature when the temperature is fixed. What do you see here? That black one is taken for the cobalt. You see very nice hysteresis curve. This is very characteristic curve of a ferromagnetic material. And the red one taken for the oxygen also follows the behavior of the cobalt, right? It is noisy compared to the cobalt signal, but it follows. It has same coercive fields, more or less same remanence signals around here, and the shape of the curve is exactly the same as the curve taken for the cobalt. So this also supports that conclusion. Cobalt sits on the zinc side in the zinc oxide lattice and makes bonding with oxygen. So oxygen is magnetic due to the neighboring cobalt atoms. So this is very nice property, and as I told you, no other method can give you that information. XRMS is very, very powerful method to investigate magnetic properties of the materials element specifically. So with that one, I finish my lecture.
I have a question.
Please.
All the measurements were taken at room temperature 300 Kelvin, right?
Yes.
How about, you said at the beginning of the lecture, we can change the temperature at the diffractometer.
Yes.
So if we change the temperature because paramagnetic materials affects on temperature, maybe oxygen shows more magnetic susceptibility at any temperature other than the room temperature, right?
Okay. Okay. So you can also carry out low temperature experiments, and indeed we did low temperature experiments for many materials in the past. But for that case, even at room temperature, we have very nice signal from the cobalt and very nice signal from the oxygen. Okay, so it is not necessary to go to low temperatures. If you cannot see good signal at room temperature, of course you can go to the low temperatures. And for sure, at low temperatures, the magnetization will be higher for the ferromagnetic materials. Okay, so if we plot the magnetic susceptibility of the ferromagnetic materials, we can plot like this. This is the susceptibility. This is the temperature in Kelvin. Okay, so I can plot like this. This is Curie temperature, let's say, for ferromagnetic materials. Susceptibility is like this. Okay, so it goes up, and here within that range they show ferromagnetic signal. This is valid for the ferromagnetic materials. Above that temperature there is a paramagnetic order or magnetic disorder within the material. For the cobalt, this Curie temperature is huge. Okay, it is, if you are talking about metallic cobalt, this Curie temperature is around 1400 Kelvin. Okay, we are talking about 300 Kelvin. We are in that range for the cobalt. Okay, but sometimes, of course, as you mentioned, low temperatures are required to investigate magnetic properties of other materials. At low temperature, the mechanism is same. Measurement steps are also same, okay? But you have to be careful with the ice formation on the surface of the material at low temperatures. If the vacuum of the system is not good, then there will be ice formation on the surface of the thin film. Then you will have difficulties with the sample alignment, okay? Because there will be diffuse scattering due to the ice formation on the surface. So at low temperature, I mean, you mainly must be very careful about the ice formation on the surface. Then other things are same what you are doing at room temperature. Any question? Then I finish with that part. So next week we will continue with X-ray magnetic circular dichroism, and I will also go to detail of that features, high intensity for L3H, low intensity for L2H, and I will explain two-step model. Okay, why do we see magnetic signal from the ferromagnetic materials?